Hi. So in this video, we're going to talk about linear combinations of vectors. But before we get there, we're going to define what it means to be a subset of a bigger set. So let's do that definition first. Let X and Y be two sets. So yeah, that's a period. And then if X is an element of Y, for all X in X. So if in this case, we're going to be seeing vectors, but if object X is in the set Y for every single object that's in our set X, then X is a subset of Y, and we write X, and it's going to look like a less than or equal to sign, but very rounded. So oops, X is a subset of Y. There we go. So let's do a couple of examples to see if one set is a subset of another, just to make sure we're comfortable with this. But the idea is X is a subset of Y if everything in X is also part of Y. So this is going to be example 5. Did I just write on myself? No, I didn't. That is good to know. Example 5. We're just going to do true, false. Decide if these are true or false. So the first one, we've got the set containing X squared and X plus 1 is a subset of P2. And then for part B here, we have the set containing a matrix of the form A0, 0B, 0, 0, so that A and B are reals, is a subset of M32. So these are the two problems we're looking at. Take a moment and decide whether they are true or false. Has a moment passed? Feel free to pause if the moment wasn't long enough for you to kind of think about this. So I'm going to say that A is true and B is false. So here's why. If I look at these values here, I have to check that each of these are elements of P2. So X squared, that's a degree 2 polynomial. I could think of this as 1x squared plus 0x plus 0. Right? So that's in P2. And then X plus 1, I could think of this as 0x squared plus 1x plus 1. So it also fits the mold for P2. So this is a true statement. Hooray. B is sneaky because if I had put M23 here, it would have been true. So this is false because this is a 2 by 3 matrix, not a 3 by 2 matrix. What this is saying basically is this is giving us a form of matrices that we can look at. So if this had been 3, 2, sorry, if this had been 2, 3, because it was 3, 2, if it had been 2, 3, then it would have been true. Because every matrix that has this form, this would be things like 1, 0, 0, 5, 0, 0, right? So anything that has zeros everywhere except for these two places, excuse me, is what's contained in this set. And that is a subset of 2, 3, but not 3, 2, because 3, 2 is the wrong dimensions. So this is a definition we're going to be needing shortly. So I just wanted to make sure we got it out of the way early. So now that we have an idea of containment and subsets, let's talk about linear combination. So remember with our basic definitions of what a linear combination is, it's any object that you can get from the objects that you have. That's what it is. So let's define that formally. So this is definition 3. We're going to let V be a vector space. So let capital V be a vector space. And we're going to have a set containing V1 through Vn. These are vectors. This is going to be a subset of V. A vector, now I'm just going to call this V, is an element of big V, is a linear combination of the VI's if there exist AI and R so that V is equal to A1 V1 plus yada, 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 AN VN. In other words, to be a linear combination of vectors just means that if I take any scalar multiple of the vectors and I add them together, that result is the linear combination of them. So let's do an example of writing one vector as a linear combination of some other vectors. So I think I should be able to fit that underneath here. So let's try. So this is example 6. And I'm going to consider the set containing x squared, x, and 1. And this is a subset of P2. So each of these are a degree 2 or less polynomials. So they are elements of P2. And let's write P equals the quantity x plus x minus 3, squared, as a linear combination of these vectors. Okay, so to do this, what we're going to need is we're going to have to say, okay, if I take this vector P, how can I write it so that it is something times x squared plus something times x plus something times 1? That's my goal. So in this case, that's pretty easy. Actually, we just have to write this in standard form. Remember that you can't distribute exponents. So if you want to FOIL this out, you can. But when you do that, you end up getting x squared minus 6x plus 9. So if I'm going to call this one V1, and then this one V2, and then this one V3, just so we have similar notation to our definition up here, then P is going to equal, I have 1x squared, so I have 1x squared, so that's going to be 1v1, minus 6x, so that's going to be minus 6v2, and then we have plus 9 times 1, so plus 9 times v3. And that's it. So all we had to do was figure out how to write P in terms of these 3 pieces here. So I purposely wanted to pick an easy example for us to start out with here, because actually, if it's like quite tough, it gets a little bit tougher to do. So we're going to see that in a future video. For now, that's it for this video. Just a quick introduction to linear combinations. And in the next video, we're going to see where linear combinations really shine when we talk about the span. So I hope to see you then. In the meantime, have a great day. Bye.